Right, so our next speakers are Marco Hutter and Christian Gehring. Both are co-founders of Robotics in Switzerland. Currently, Marco is a professor of robotics at ETH Zurich, and Christian is the senior director of robotics at Robotics. So excited about this talk. I've paid attention to quadrupedal robots over the past decade. I think their groups have been responsible for among the most impressive results, both on the commercial and academic side. So excited to hear what they have to say.
Great. Ready? No, it's not ready. Thanks, Scott, for a nice introduction. So we thought about giving you like two views on that problem. On one side, from me, more from a research perspective, and what can we do from a research point of view to bring things closer to our application. And then Christian, he knows a lot more about how to be certified these things and bring them to a real world product. So he's going to do that in a second phase. And we also switch gears a little bit to the previous presentation in the sense that what we see here is not only about software, there's also a lot about hardware and how software and hardware both come together. To give you a little bit of an overview of what we have been doing in the past decade, so that's kind of the research that we have gone through, and then the whole productification until like fully certified quadrupedal system. What we have been starting with is really making simple prototypes in the lab with like all kinds of safety systems you can imagine to just like study the fundamental principles. We then went a lot more towards how can we robustify that, and instead of having it just tested in the lab, bringing it to the real world to do some field robotics, but still field robotics in the research context. So when we talk about these kind of systems, then we're more about like figuring out what can be done, what not, moving the researcher level higher up instead of like just dealing with locomotion, dealing also with autonomy, environment perception, stuff like this. And then the last step, and you see how long this took, right? So it's going to be like more than 5 years between this level to have like a fully certified system that today is doing industrial inspection on different kinds of facilities. This machine is like fully IP67 certified, proven, has CE certification. And the latest generation that we just released about 2 months ago, has also ATEX certifications that can work actually in explosive environments. The differences in how they're moving around is not that big of a difference, but still like there's a huge change between these platforms. All these individual iterations that are complete redesign more or less from scratch. So let me start a little bit, formulate what are the challenges that we have in the research perspective. I think first of all, we try to group that in like 3 different layers. The first layer where most of us researchers work in is that you're doing research, foundational research in the lab. You have individual researchers building their own robots, operating their own robots, so they know pretty much everything about that. They can run and debug a fragile system. Then you have typically very careful operation in that. So they treat this robot like a baby. You don't have to worry about somebody destroying it because you know that person also has to fix it afterwards. And then the last point, that means also that people take a lot of care about their systems. They also try and tune the environment problems to the skills that we have in the robotics. That's all great, and we can move on with that, but I think it's not sufficient to move or bring robots to the real world. We have to have a second level. At the second level, this is still happening to a large extent in academia, also connected a little bit to industry. In how can we bring now this robotics research to the field? I'm going to go into a couple of examples in relation to the Star Basati competition that we participated in the last couple of years. So what you do have here is still expert researchers with a little more advanced robots, but they still know sufficient that they can at least code on these machines and they can do simple maintenance. They know about the pros and cons of these robots. They do careful operations. They handle the robot with care, but they still push it to the limits because you want to do some field deployments. The big difference is now no safety harnesses anymore. You have a harsh environment. The robot has to somehow survive. And then the third level, and that's actually the big difference now, is that you want to give a product to somebody, and that product has to be certified because you have non-expert users. they can't fix the robot, and also they don't want to fix the robot. The robot itself has to be robust enough. They also, there's unintentional, but also intentional operation to either go or at least try to go with the robot beyond the limit. So everybody has a bolt in their hand to try to make it fall in one or the other way. And we have to somehow deal with that. And the third one is also, again, like no safety harms. And we're going to do two talks here, two short level steps. First one is I show you how we can go from level 1 to level 2, and then Christian will make the second part from level 2 to level 3. So for me, one of the most important objectives or tasks that we have also as PIs in this field is that we can motivate for field deployment. And that's not that easy because the problem is that field deployments are expensive. It's not that rewarding for your PhD student. It doesn't give the best scientific paper. And it takes a lot of work to make a great scientific paper, but it's still essential to move the field forward. The question to me is a little bit like, how can we motivate this? One thing is you fool the PhD students by giving them extremely nice challenges in extremely nice environments, such that they get rewarded also by what they're actually doing, and not only by having this great scientific work behind them. You see here a couple of examples in where we're deploying our machines. And the second element, and I think this has gained quite a bit of importance, is that we're having challenges. We're having competitions where things are tested in the field. And the nice thing about this is that whatever you show in a paper is just showing what works once. But when you go to competition, then you realize what does not work. And I think this brings us way more forward than just like talking to everyone and they say, yeah, it's working, but then it's really not working. So we did lots of competition in the past in all kinds of different conditions. I'll give you some glimpse into that. So try to collect a bit of do's and don'ts when we move from this level 1 to this level 2. The first don't is that you should never think that a research platform is a field robotics platform, and that you could ever convert this into a field robotics platform. Field robotics platforms, they have to be designed from the beginning like that. When we did our first quadrupeds, they looked like this very nicely in the lab environment. We could operate them, and then we took them into the field, and then they looked like this. It's getting kind of a Christmas tree. You start adding different sensors, and you realize there's no safety system anymore, so I start adding bumpers, and it just never works. So you bring that to the field, and you have even people walking next by. So that shows a little bit the very, very early field deployments of some of our machines. Nonetheless, you learn a lot with doing this, so you have to iterate over it. Second thing is be ready ahead of time. Forget about any kind of last second integration. There must be a very early feature freeze, and we have to forget about any kind of on-site integration. When we went to field trips some years ago, it always looked like this. We had a van packed with all kinds of equipment and a robot. Now it changed a little bit in the meanwhile. On testing sites, when we went for a week on a competition, looked like this. So we actually had to really fix things a lot, even on the way, and that's just never working out. We changed a lot in this regard. For example, in the DARPA sub-T competition, we had on the hardware side, like 6 months before the competition, there was no hardware change allowed anymore, and we knew this ahead of time. So whatever was there, that's it. And 3 months before the competition, there was no external software update anymore. So if these guys pushed a new version of some part of the code, we did not touch it anymore. And then 1 month before the competition, no additional feature, no longer. And then you just like fine-tune this to make it. Then a couple of tools that we started to embed at the lab. First, shakeouts, feature freeze, integration tests. So what we did do is like whenever there's new things coming in, we did test the single components in the lab. Then we had some mock-up missions and tests that we could like easily access on almost on a daily basis. But then you also did like regular integration tests. And for these integration tests, it's very important that you're not doing this at home. Go somewhere out, because then you realize what you have to take with you, what it makes to make the system run there, and it takes a lot more than what you think when you're at home. During the sub-T, we did every Friday. It was like a test of the new features, and the shakeout of everything was there. So kind of a mock-up mission, like testing everything. And we did more than 20 field tests in 5 different sites as a preparation for that. Then you have to start thinking a lot more like a company. So we start using tools and organize our research with like project management tools like Write and stuff like that. Make sure that you distribute responsibilities, meetings, sprints, and integration weeks. There are a couple of them all the time. We still do this, so even without the competition, we do that every couple of months. And apply also rules, simple coding standards, how do you pull requests, code reviewing, continuous integration. Make sure that you have not all the students having their own parts of the code and never bring that back to master anymore. And also as a team, act as a team, as a lab. So we do like the whole lab in 1 week, but there's a new software release, new ROS coming out, new Ubuntu upgrade, the whole lab should do that in a short time frame. And then the last element, I think it's always important when we think about field robotics, that we better use a well-oiled engine than something like highly superb. Because in the end, fence is great for a paper, but what is really important for field deployment is robustness and reliability. And this I hand over to Christian for the second part.
Right, as Marco indicated before, academic research requires the development of technology with a different focus than what is required for industrial applications. So researchers are interested in pushing the boundaries of state-of-the-art. They are developing innovative and novel solutions to publish their work at conferences and journals, etc. So this leads typically to systems with a technology readiness level of 0 to 5. So the systems are tested in simulation lab and sometimes in the field. In industry, there are additional objectives and requirements that need to be met. So users of robots, they're interested in the value of the application of the robots on functionality, robustness, and reliability. They want to invest as little money and time to operate and deploy robots, and they want to minimize and limit the risks in terms of safety and security, and they want to make sure that the system is compliant with regulations. So what we need is to build systems that are qualified and complete and have a technology readiness level from 8 to 9. So researchers at the university, we always push, the hardware to its limits. We run actuators out of specs. We are adding sensors like hell, lots of sensors. We've seen the ETH's version of the Darwin Challenge. So it's an animal with additional lidars, additional cameras, and also graphical cards. So they use state-of-the-art commercial computing systems. They use mechanical designs with really low safety factors, etc. And in industry, we design to specs, right, for lifetime cost. So we need to use industrial grade components. So we saw this with SSDs. You don't want to use commercial SSDs. So the industrial ones are more expensive, but they're really worth the money. We need to make sure that the components are not just available now, but also in the future for a few years, right? We want to avoid single source of supply. So sometimes that limits us to integrate the cutting edge technology. To use robots in industrial environments, in outdoors and in dirty environments, you really need high inverse protection. So we designed the system for IP67, and at university we already started to do that, but then we just put it into water and that's it, and we were happy that the robot still worked afterwards, right? But at Antibiotics, we really need to do systematic tests. We need to follow procedures from standards and to really claim that it's IP67. So we see on the right, there's a tank where we put the motor inside and let it run. It still needs to work. You can see whether there's water in the device or not. We built a new version of the robot. It's the first certified robot for explosive environments. So you want to limit the risk of an explosion of the gases that are in the atmosphere by this robot. So what we do is we fill the main body with nitrogen gases, and we add flame gaps to the actuators so that the flames cannot leave the housing and ignite the gases outside in the atmosphere. So you see here, this is one of the tests. You really need to fill the actuator with explosive gas and then ignite it. And that's a standard procedure that a notified body has to check Like robots, it's essential to build them as lightweight as possible to extend the reach, right? But on the same time, you want to build them rugged, robust, so when they slip and fall, eventually they can get up again, but they should also not break at that time. So if you apply conventional engineering rules, you come up with very bulky and heavy designs. So what we need to do is build the system in an iterative approach, so trial and error, and really test the systems, protections, etc. Robust perception is also essential to overcome obstacles and avoid obstacles for our systems. And you know, in academia, you typically want to develop solutions that generalize well. Right? But in industry, we typically need to often custom engineer solutions to increase the success rate and robustness of these solutions. So here we were applying filters for semi-structured environment, knowing that this might not be optimal in you know, highly unstructured terrain like in mines, etc. But here it works better than the generalized solutions. Then we always verify the design, so we design to requirements and then check whether we fulfill the requirements. And we need to do that also for certification, for reliability and robustness. So we put the robot on a shaker to do vibration tests. The robot needs to operate in a large range of environmental conditions, so that we test it in a climate chamber at high temperatures. We run highly accelerated live tests to investigate and analyze earlier failure rates of the hardware, etc. Of course, we have to also check for electromagnetic compliance and immunity. So, as Marcus said, the best operator of the robot is the developer himself or herself. Right? But in industry, the users of these robots, they neither have the robotics expertise, nor do they want to learn how to do robotics, and so we need to design user interfaces that are very simple. We always try to combine the best of the human operator together with the best of what the robot can do. So intuitive control is key to reduce training time of the system, which is also quite essential. So on the right, you see this is a tablet that is certified for explosive environments. So it's very heavy. You need to hold it with one hand. You need to use gloves, etc. So if you design a system, you need to consider that as well, not just using any toy pad that you typically have in industry, in academia. Safety is a huge topic. We can talk a lot about this, right? Legged robots, from their nature of locomotion and the environment, they have some unavoidable risk. So the robot can always kick stones and shoot them around. It can trip over cords and fall down. So their most prominent hazards is that if the robot actually falls down due to loss of stability, or they tip over, etc. And so they need to continuously balance, right, to keep their slippery terrain and so on. So that means they need to always continuous power and do fast movements to keep the balance. And that means also sometimes they need to step to the side, etc. So powering off and locking legs are kind of not two good solutions for like robot. Imagine the robot is on stairs and it locks its leg because of an error, or you power off and it can fall down the whole staircase and hurt somebody that is on the staircase. So common safety measures for quadruped robots nowadays is that we introduce this kind of a keep out distance when the robot is actually moving around. So there's an indicator light showing the operator that it cannot approach the robot in that sense. And we employ control strategies that prefer to fold the legs and lower the center of gravity to avoid falling down. The safety risk depends really on the intended use. So it's not just the robot itself, but it's the environment and what it's supposed to do, right? So quadrupeds are today mostly evaluated using first principles. So you do a risk analysis, you identify hazards and so on. And what is also important is the probability of exposure of this risk. So we are using the robot in industrial environments where there are typically not many people around, or they are instructed people, etc. And the users can really shape the exposure time and by shaping the environment and tasks that the robot needs to do. So in the end, the user defines the acceptable risk and has to implement a final risk assessment together with the robot. Our robot animal can be operated remotely, so it can be connected to various other systems like digital twins and so on to report automatically inspection reports. But that means that the robot needs a secure system design to prevent criminal activities. And different technologies require different or have different needs. So IT systems, typically, it's important to protect information and data. So it's about confidentiality, it's about integrity and availability of the data. While in industrial processes, it's important to monitor and control those processes, right? So control and availability is much more important. And with robotics, we have actually an additional layer, namely safety. So you can use the robot, you can hack it, and you can hurt people with it eventually. So that safety and security are interlinked for robots. So we need to implement a number of security control mechanisms to, for instance, permit access to the robot, to control from remote, etc., and so on. So that's an additional layer you need to care about if you go into industry that you don't need to take care of in academia. So when we build our product, we are trying to solve problems that are active topics in research, right? So that's why we are also evaluating a lot of papers. And so what we saw, if you look at these papers, typically important stuff is in the details, and those are typically not in the papers, right? If you provide open source software, that's great. You can figure out better what you're exactly doing. But still, what we do is we implement the proof of concept. So we typically bug fix the code, evaluate the performance, and so on, profile code for quality. But most importantly, we are really testing all the corner cases that are important for our application, the benchmark the solution. So you can get a working solution rather quick, but then to achieve a minimum viable product, you start with the development, and typically you start from scratch again with code. And then you test in simulation, you do the whole software stack integration, and then you really start with the software quality assurance. And you, of course, need to add user documentation, tests, and training, etc., that you typically don't do in academia. So software quality assurance is super important for us. We're following a DevOps philosophy and have a number of tests and quality gates in place. So when a developer is, coding new stuff, then he typically tests it manually on robots. Then we have a number of integration tests that are built automatically in our build service. So before you merge stuff into master, you do peer reviews, which are really important, but you also get a dashboard with some KPIs that shows you the test coverage of the code, etc., and so on. And then what we do is daily system and deployment tests. We use physics-based simulation. That's also on the build server. We do build tests, etc. So, and then on the weekly side, so every Friday, people take the latest cutting-edge software and test it actually on the robot. So hardware-in-the-loop tests. They're semi-automated, so you go through a huge test protocol. You have some stuff is automated. You get, metrics that are important, etc. So we have this kind of test mock-up in our lab where we run full inspection tours. And then, of course, before you ship the code, you have again release tests, another set of tests that you need to go through, like safety critical tests, etc. And then, last but not least, we have also reliability tests. So in our dungeon, in our cell, we're running, let some animals run all the time, 24/7, to check that things work also over a long period of time. So with this, I hope we gave you some valuable insights how we do stuff at Robotics and ETH, and what is needed to deploy robots. Thank you.
any questions for Marco and Christian? Heard you use the microphone. All right, I have one. Are you using a learned controller in any of your product offerings?
Yes, we do. It's our stair plan with motion resolving also.
And what do you view as the for going forward? Do you feel like there's going to be just more and more of that, or do you feel like there's just a well-defined space for that type of
I think you know, for us, this is just a tool, right? It's one approach, and model-based control approaches also have their pros and cons. And so I think, yeah, we do more and more. It's really machine learning, like also the inspection intelligence is typically machine learned approaches, and I think it's playing over. So yes, we see a clear direction, but and you see also lots of paper and a lot of research is going on. But the problems are not solved fully, right? Like I can tell you a number of sites that where things don't work with our current solution, but we still have good work to do. It's great to be an engineer at this time.
Actually, I have a question, if you don't mind. A lot of what you're doing is focusing on compliance. Can you maybe give some lessons learned, or what was the greatest insight or something that you would suggest to anybody looking to industrialize their solution to actually address first, so they don't have to perhaps have a very long kind of cycle of getting these things through?
Well, I think it's really useful if you have a person that is used to compliance with those topics well, so at least how that thing works, right? So you have a number of standards, you have different, every country has their own regulations, etc. And nobody knows how to deal with this kind of machine, right? So having somebody that can prepare the documents and so on, so working together with an agency helps for sure. So I mean, for European Union, you do basically self-certification, but we don't do that on our own because we're also not experienced in that sense. So getting support there, that's definitely helpful. And then, yeah, you have to figure out this channel works for you and whatnot. And if you just follow the agencies, right, they will. That's their business, right? To get paid, so you don't believe everything. So keep things simple. But it's also important to understand really what are the needs of the customers, of the people that want to use the robot.
Any other questions?
What tolerance
So what we do, we have to, because we still need to do hardware and loop tests, so we're not just a pure software where we can do continuous deployment, right? So that's why it's limited to, I mean, at the moment we're at like twice per quarter, 3 times per quarter we can release, it's fine. You could increase that, and the features are basically, so a number of features will take longer and some quicker, so that doesn't matter. And for hardware, you need to go, it's a longer process because you need to also, make the drawings in production, etc. And then you need to train the production people to actually build it. So that's actually a much on the side.
question about performance? So you're talking about how you're going to show these world models.
So, I mean, we're really testing them in all kinds of scenarios. So, nice thing about this solution, it's never, people are sometimes scared that it freaks out and so on. And I've seen that with model-based control, optimization crashes, and the robot freaks out. And with these machine learning methods, I haven't seen that crazy behavior. So that's good. So it gives us good confidence that we can use robotics.
All right, well, let's thank our speakers once again.